do it justice here. We'll be going through the topic 11 review. And once again, like the last few, I don't have the answers here with me, so I might be a little bit slower than normal in finding these answers, but that's all right. We can keep going through and it should be all good. So starting with number 5, says the pyramid has 6 vertices and 10 edges. How many faces does it have? We're going to use Euler's formula for that. So faces plus vertices equals edges plus 2. We've got a number of faces plus 6 equals 10 plus 2. Obviously, that means that the faces is 6. So it has 6 faces. Number 6, visualize a plane intersecting the pyramid parallel to the base. Describe the cross-section. Well, that means that this intersecting plane would intersect at a pentagon, just like that. Would go parallel. So it says describe the cross-section. It is a pentagon. Number 7, describe the 3-dimensional figure that is formed by rotating the rectangle about the line shown. If we rotate that rectangle, we're going to get a cylinder that kind of looks like that. Oh, goodness. I'm not going to be able to draw it well, but just like that. So that is a cylinder. Number 8, can a polyhedron have the same number of faces, edges, and vertices? Explain. Well, that's interesting. We would have to make that Euler's formula to see. So faces plus vertices equals edges plus 2. But if the faces, vertices, and edges are the same, we could call that x plus x equals x plus 2. Simplify for 2x equals x plus 2. Subtract x from both sides would give us x equals 2, which tells us that if the number of faces, the number of vertices, and the number of edges was 2, then that would work. The problem there is we cannot have a polyhedron with 2 faces or 2 edges or 2 vertices. That's too small. The smallest polyhedron we have has 4 faces, and that is the tetrahedron that's made up of 4 triangles. So this is not possible. Not possible. No polyhedron has this few of any of these. No polyhedron has this few faces or edges or vertices. Numbers 9 and 10, find the volume of each figure. We've got some prism cylinders here. So we've got for number 9, pi times the radius of 15 squared times 70, and it says round to the nearest tenth. So let me put these in my calculator. So another reason I'm going to be slow here is because I have to put all of the answers into my calculator. 15 squared times 70. It's going to be 49,480.1 if we round to the nearest tenth, and that would of course be millimeters cubed. Number 10, we have an oblique cylinder, but it's still going to be measured the same way. Pi radius is 3 squared times the height of 8. So that's going to be 226.2 yards cubed. Number 11, what does the expression 3/4 XYZ represent for the prism shown? Well, if we are going to calculate the volume of the prism, maybe I can do that and then compare it to this expression. So if I calculate the volume of the prism, we would do the area of the triangular base multiplied by the height So that would be 1/2. Area of the base is base times height. So 1/2 z times 3y multiplied by the depth or the height of the figure. So that's x. So let's see. 1/2 times 1/2 is 1/4. And we have a 3y. So it'd be 3/4 x, y, z. And it says, what does the expression 3/4 x, y, z represent? So it must represent the volume. Volume of the prism. Number 12, Malia pours wax in molds to make candles. Compare the amount of wax each mold holds. Ooh, we have a hexagon here. So we're going to need to figure out the area of the hexagon in order to find out the volume. So let's see how we can do that. It looks like we have maybe being shown here 2 trapezoids. So let me draw the overhead view of this in a way that maybe my program will recognize it as a regular hexagon. There we go. So, yeah, okay, I'll keep it like this, I guess. So when we've got this regular hexagon, it's kind of showing us that across the middle is 16 centimeters, and this is 5 centimeters on both of these sides. And then the dimension all the way across here is 14 centimeters. So if I were to measure the height of one of these, it'd be 7. And the height of the other one would be 7. So this is going to be 2 trapezoids. I know how to measure the area of a trapezoid because I'm going to do the average of the bases. In this case, our bases of the trapezoids are 5 for the short base and 16 for the long base. So that's going to be 5 plus 16 over 2. That'd be the average. Multiplied by the height of the trapezoid, which is 7. But I have 2 trapezoids together that make up the base. So I'm going to need 2 of these, 2 trapezoids for the base. And then if I find the area of the base using this expression, I'm going to multiply it by the height, which is 18, the height of that hexagonal prism. So if I do all of this, the 2 and the 2 actually cancel out. But once I put this into a calculator, I'm going to get 2,646 centimeters cubed. For the other one, of course, it's just a rectangular prism. So 21 times 7 times 18 equals also 2,646 centimeters cubed. So they are the same. Interesting stuff there. All right, next we've got some pyramids and cones to deal with. Both are oblique, but that doesn't matter in our volume calculation. So for 13, we're going to do 1/3 times the area of the base, 12 times 4, times the height of 7. So that's going to be 112 inches cubed. For 14, we've got 1/3 times the area of the base, pi times 15 squared, times the height of 24. So if we do that one, that's going to be 1/3, putting it in my calculator, pi times 15 squared times 24. Going to be 54.9, right? 0.866, but it rounds to 0.9, and that's meters cubed. All right. Number 15, a sculptor cuts a pyramid from a marble cube with volume t cubed cubic feet. The pyramid is t feet tall. The area of the base is t squared feet squared. Write an expression for the volume of marble removed. This is interesting. So there is a cube of marble. So let's draw a cube of marble in maybe a way that my program will recognize this as a square. Perfect. Got our cube going here. I was so close to getting that perfect. Oh well. So on this cube, it says the volume of the cube is t cubed feet. So we know that that means the length is t, the width is t, and the height is t, because the volume of a cube is length times width times height. The pyramid is t feet tall, and the area of the base is t squared. So maybe the base that gets cut off is this one, and the pyramid itself, let's see if I can, oh goodness. The pyramid itself is going to come down into the center and connect to each of these vertices, just like that. So we're cutting a pyramid out of the center of the shape. So it's kind of going to have a hole in it, because that pyramid has a height of t, since it's the entire height of the cube, and its area of its base is t squared. So our expression for the volume of marble removed would be a volume of a pyramid, so 1/3 times the area of the base, t squared, times the height of the pyramid, t. So 1/3 t cubed would represent the volume of marble removed. Number 16, a company cuts 2 inches from the top of the solid plastic cones. How much less plastic is used in the new design? So we need to figure out what is the volume of plastic just on the top of the cone. All right, so that means that, let's see, it has a radius and a height. We don't even need to use these bottom ones, because we're just saying how much less plastic is used. So we're figuring out what is the volume of removed plastic from the top. So that would be 1/3, because it's a cone, times the area of the base, pi, times 3.5 squared, times the height of that removed section, which is 2. And if we calculate that, 1/3 pi 3.5 squared times 2, we get 25.6. And if we're rounding to the nearest tenth like we're doing for the rest of these, it's actually 25.7 inches cubed that is removed. How much less plastic is used? There's 25.7 inches cubed less plastic when we cut the top off that design. Numbers 17 and 18, finding volumes of spheres. So for 17, we've got 4/3 pi times the radius of 1.2, because they gave us the diameter, cubed, right? That volume formula, 4/3 pi r cubed. So if we calculate that, we get 7.24. Round to the nearest tenth, 7.2 inches cubed. For number 18, we only have half a sphere, so instead of 4/3, we'll use 2/3 for half the sphere. Pi times the radius of 0.9 this time, cubed. And that is going to be 1.5 centimeters cubed. So some smallish spheres here. Number 19, a golf ball has a radius of r centimeters. What is the least possible volume of a rectangular box that can hold 2 golf balls? Well, let's draw a rectangular box that can hold 2 golf balls. So here's a golf ball. And here's a golf ball. We'll put them right next to each other. How do we put them right next to each other? Oh, come on, I know how to do this. There, move them just like that. And if we are making a rectangular box that can hold them, then we've got to draw this rectangular box around them. Just like this. We're going to imagine that it's tangent, that it's touching those sides. Ah, it's so close, but it's not quite like that. Let's try this again. There. Overshot it. I'm being a perfectionist, but that's okay. Whatever, good enough. And so then it's got to go out this way. And obviously, you're going to be able to see the balls from all the sides because they're going to touch on every side. So if the radius is r, that means here's the radius. So there's 2 radii going across, 1, 2 each ball, and then another 2 here. So there's 4 radii across the long side. The height then would be 2 radii. And the depth would be the diameter of one of those golf balls. So that would also be 2 radii. So the least possible volume would be 2r times 4r times 2r, length times width times height, which is going to give us 16r cubed. We don't know the r, so we'll put it in terms of r. Number 20, a capsule of liquid cold medicine is shown. If 1 dose is about 23 milliliters, how many capsules make up 1 dose? So we're going to need to figure out how many milliliters this capsule is. And it looks like it's made up of 2 hemispheres, so 1 sphere, so 4/3 pi times a radius of 1 cubed, plus a cylinder, which is going to also have a radius of 1. So that would be pi times 1 squared times the height of 0.5 centimeters. So when we calculate this together, we're going to find that that is pi times, so I mean this part is just 4/3 pi. And then this one is 1 pi or 1/2 pi. If I add those together, 4/3 pi plus 1/2 pi. Oh goodness, 4/3 is the same as 8/6. 1/2 is the same as 3/6. We get 11/6 pi, which is the same as 5.6. No, 5.76 centimeters cubed. Since we know 1 centimeter cubed is 1 milliliter, then this is 5.76 milliliters. And if 1 dose is 23 mils, we'll do 23 mils divided by the number of milliliters in a capsule. 5.76 equals 3.99, which is around 4 capsules. And there we go. Let's see what else we've got here. Extra practice. 21, a polygon has 20 faces and 12 vertices. How many edges? Gotta use Euler's formula. 20 faces plus 12 vertices equals edges plus 2. So 32 equals edges plus 2, which means that there are 30 edges. 22, same idea. We've got faces, 8, plus vertices we don't know equals 15 plus 2. So 8 plus v equals 17. That means vertices, there are 9 of them. And another one, we've got 16 edges and 10 vertices. So faces plus 10 equals 16 plus 2. Faces plus 10 equals 18. All right, and that means that faces, there's 8 of them. 24 and 25, just some simple finding volume. So 24, we've got 1/3 area of the base, 9 times 9, times the height of 12. So going to be 324. For 25, I've got pi, well at first I have 1/3, pi times the radius 7 squared times the height of 21. That's going to be 1077.6. Since we rounded everything else to tenths, we'll round that to tenths. And finally, this composite figure has a cylinder on the bottom, so pi times 10 squared times the height of 12, plus a cone on the top, that's 1/3, times pi times the radius is still 10 squared times the height of 10. So that would be, let's see, this is 1200 pi. Plus, and this is 1000 because 10 squared is 100 times 10. So 1000 over 3 pi, or 333.3 pi. So we end up with 1533.3 pi, which is equal to 4,817.2. All right, and that is all we have here. Hopefully that helps you out and you'll be ready for the test on Thursday. All right, have a great day. I will see you later. Bye.